I'm Roy. I'll be talking today. I'm at Harvard. I work with Seth, Neil, and then Syl Vadan, who's a theory privacy person. Um, and for this project, we also worked, so it's me, Seth, and then a postdoc, Shivam, and then we also worked with the Madry Lab, Chris, Sam, and Andrew, as well as Madry. Not important to do this now, but if you wanted to follow, you could. And then, yeah, so we're going to talk about unlearning. This is my favorite tweet related to unlearning. I feel like it captures, I don't know, what even is unlearning? Okay, so in this talk, we're going to kind of do we're going to talk about high-level goals, challenges to unlearning in general, and what the existing methods are. We're gonna kind of ask like, how would we do this perfectly? How would we cheat if we could do it? And then we're gonna say like, oh wait, we can't cheat. Like let's do it for real. And so to start, what even is unlearning, and what is success in unlearning? We have to take like one step back and ask. People mean a lot of things when they talk about unlearning, and there's kind of this at least three big categories. One is exact unlearning and approximate unlearning. Exact unlearning is where you like basically fully retrain your model or find some way to checkpoint your data in some way that you don't have to fully retrain your model, but you have removed the data from the model. It's perfect. You can't really argue that. Now what we're going to be talking about. We're going to be talking about approximate unlearning, where you're trying to like find a cheat code from the model that you have now to a model that never saw data. And within that, there's kind of two things that people might talk about: concept unlearning and data unlearning. Concept unlearning is like, I want to forget, the concept of Harry Potter or like the concept of Alex. And data unlearning is like, here are specific pictures, and I want you to simulate what would happen if those pictures were never in the training. They're related, they're hard and different. I'm going to focus on the second one. Okay, so what is data unlearning? I like this diagram. It's okay, so you trained a model, and now you want to remove something from the model. So you really want this model, not that model. But you don't really want to fully train. So you want some like shortcut between those two things. So there are different reasons why you might want to unlearn. These are commonly cited runs: removing copyrighted data, privacy, and poison data. And it's important to like know why you're different reasons for unlearning dictate a lot. As like a small table, you might say like privacy, like there's this legal requirement, GDPR, I have to do this. How do you unlearn? There, the like measure of success is that your model looks like a model that never saw the data. But if you have poison data and you're just trying to remove that, you want to unlearn the poison data, you don't care about that. What you care about is just, did the poison get removed? If you have bad data, you just care about if the model improved. And copyrighted, I think this is like this is fundamentally a legal question. This is an opinion, but I think this generally is a process-driven question, not like lawyers most likely will not accept a statistical guarantee or a statistical like empirical measure, and will probably just say, was this data ever in the data set? But that's an opinion. Don't take that too seriously on that last one. We're going to focus kind of on this privacy thing, but they're all kind of related. And if you want me to talk about something, please interrupt. Why is measures of success? Why are we like spending so much time on measures of success? It's because they like really matter. Your measures of success really matter, and learning can hurt you if you're not careful about what you're measuring. Like if you're learning for poisons, imagine this concept, like there are poisons that people have developed where you can put 2 data points in a data set, and they don't have any effect. But if you were to remove one of them, the poison is revealed. And so if you did perfect unlearning on that second point, you have like poisoned your data fully, even if you were doing the perfect unlearning of just fully retraining. Obviously this gets like, this is obviously hurting you. There's like pretty strong, for privacy, there's pretty strong evidence that like unlearning one point actually worsens the privacy attackability of other points. And so if you're not careful, protecting someone actually hurts other people. And so you have to be careful about that as well. I'm going to skip this third point. It's a little more nuanced. And generally, in the world that we're going to be living in. The like measure of success is like, okay, you have this training data, you've trained your model, and then someone's like, hey, I know rabbits, and then you want this other model to basically look like, if I trained this never on rabbits and I trained it, and then you ask how similar these models. And what this specific definition of how similar these models are is hard. I'm going to specifically talk about in the convex setting, sorry, in the non-convex setting. In the convex setting where you're dealing with models that are well defined, you can kind of define these formal notions of statistical distance. But in large models, where these are very, very high dimensional and not well defined, we can't really train a bunch of them and get a statistical distance between them. And so what we're going to do is ask for statistical similarity in output space. And I'm going to walk you through what our proposed measure is, and it's going to be very similar to existing measures. But right now, this kind of is the Wild West. There's a bunch of proposals for how you want to evaluate.
So in other words, so to be clear, so you're working in output space, not in parameter space.
That is, yeah, yes, it would be unreasonable to work in parameter space in non-convex models because they're too big and they're just not parameterized well.
So there's all these like influence function people who sort of work in parameter space, even though the models are so bad. And it's sort of related to your thing. Do you have perspective on that?
Yeah, I actually will. I have a slide that might be skipped, but it is soon. That is kind of talking about that. But I think the answer is maybe someone cleverer than I can do a model space comparison, but by default is very hard. And relying on output space at least gets us a starting point. So you're going to take what we're trying to do is say, let's compare the distances between Oracle models, which are fully retrained, and things that have gone through our own process. And what we're going to propose is, okay, first we're going to collect a bunch of them. So we're going to take a bunch of these models that only trained on the retained set, train them, and get a set of Oracle models. Let's just say for context, it's like on the order of 100. And then we're going to do the same thing, except we're going to go through this unlearning process where we're going to take the full model, we're going to unlearn it, and then we're going to do this n times, and we're going to have these two sets.
So
yes,
different models in the sets are trained on the same retrained set, or
yes,
different?
They're like identical training process. Just you're hoping like these processes are noisy, and so
Okay. Different randoms.
Yeah, different random seeds. That's right. And then you're going to say, okay, for each point, we're going to define a measure on a point. We're going to say, take a single point and compute the margin, which is like the confidence between the difference in the top choice and all the others, how confidently it's predicting something. We're going to ask for the margins to collect a histogram of margins for the unlearned models and for the Oracle models. And so it's going to be these two histograms. We're going to compute some divergence. We're going to talk about KL, but it can be anything. And then that's going to give us a single number. So for a single point, we've collected a single number. And then we're going to generate a histogram of these for like multiple sets. And it sounds like we've just done a lot of work, and we have, but I'm pretty confident that I do think it's necessary. And so what this kind of means is you can say, I want to know philosophically, what have we done? We've said, I've computed a statistical measure that will compare how the unlearned model compares to perfect unlearning for a single point. And I want to ask, how does this behave on the retained set? How does it behave on the forget set? And how does it behave on a validation set? And like to give you like kind of a nice plot, there's a typo, KL divergence on cross entropy, but this is like doing nothing. If I just like truly took the original model, didn't even unlearn it, what'll happen is like, we're really similar on the validation set and the retain set, and then we're garbage on the forget set. And so this kind of plot will maybe help you contextualize what these numbers mean. 1 isn't a special number. The point is that 10 is bigger than 1. For the rest of the stock, you'll be dealing in the range of 0 to 12 roughly. And then this is like load an oracle. What if you just like compared one of these perfectly retrained models to the distribution? And it's not 0 because there is difference, but they're all basically very small numbers from 0 to 0.5.
Sorry, can you go back one slide? And what is the third thing actually?
This?
Yeah, this thing.
So this was, you define this distance measure for a single point. And
for X is X fixed for the whole histogram, or is X sampled for the?
for this histogram, yes. And then this is, so this gets you a single number at the end of this is a scalar. And that's telling you for this picture of Alex, how far are you from the unlearned distribution? And then you want to generate a histogram of how well you're doing over particular data sets. Yes. And generally we're going to be doing this over forget set, validation set, and retain set. Or like at least like 100 points from each. The reason for this is your unlearning model might behave very well on one of those, but not on, like, you want them to behave well on both points of trying to forget, but also the other ones.
So I'm still trying to understand. So
Yeah.
So
No,
your
no,
eye,
this is-
your eye here is sampling over models. Is that right?
I here.
Mm-hmm.
Yes, this is a collection. So we start off, we just get 100 unlearned models and 100 oracle models.
Mhm.
Oracles are the retrained models.
And the histograms in the middle are histograms over this 100 models
That's right.
of how they're behaving on this
Yeah.
one data point.
That's right.
And so you're saying, and by saying margin, you're saying, okay, this is how confident the model is about this point. Maybe if margins are lower, it's sort of higher entropy or something, doesn't really know much about that point. And so you would expect that it doesn't really know much about a point. It would sort of shift to the left in that middle histogram.
Yes.
Is that right?
The actual point of the why we're using margin, this could be a higher dimensional thing. It could be actually the full logits, and we can compute a KL divergence across multi-dimensional thing, but we wanted to flatten it to a single dimension. Basically the goal here is that let's say I'm very confident in my prediction that this is a picture of a cat, and you're very confident also, you also think it's a cat, but you're not confident.
I know the difference.
Yeah. But the goal here of the margin is to flatten the prediction to a single dimension.
So then you're saying that, so then you're illustrating here that you might have an imperfect forgetting method. In the perfect case, your forgetting histogram, like how the forgetting thing would behave, would be just like your retain baseline or your retain oracle. Is that right? That these in the perfect case, these histograms would be the same in the middle. Is that right?
Yes, the KL divergence would be 0 because
Because it would be perfect.
yeah, exactly. Yes.
Right. But then in practice, your forgetting method isn't perfect. So this is just a way of quantifying how
That's
it's not
right.
perfect.
That's
I
right.
see. And so you get a KL divergence, and then down below is a histogram of KL divergences.
Yes, 4 different points.
And what kind of sample of points is it? Is it points that you're hoping to remove from the data set, or is it points that are just randomly sampled over the whole data set?
Yeah, we're going to be looking at points from 3 subsets of the data set. Things that we're trying to forget, the forget set, things we aren't trying to forget, the retain set, and then validation points that it never saw. And we're going to sample randomly from those, at least for the forget set, we're going to sample all of them. But
Validation points that it never saw, you mean your forget method never saw, or just they weren't even part of the training set?
they weren't even part of the training set.
Oh, so generalization.
Yeah, because I mean, it actually won't come up that this will matter, but you could conceive of a model that actually does really well at learning on the forget set and on the retain set, but then like if you gave it a new model, it like always spits out the number 3, and then it's very clear that unlearning occurred. That's not necessarily a bad thing, but we want to know that it's happened. Like we want to, this won't be important, but we thought it would
Something to look at.
It's something to look at. The two data points we're going to be wanting is so this is that histogram before for baselines. Take a look at this one, do nothing. The blue is the forget set. So the original model obviously didn't forget set, never even tried. And so most of the KL divergences are quite far from what the best model would have done. But on the retained set and the validation set, like there was nothing it had to do.
So now some of the KL divergences are low, which suggests that maybe the original model didn't learn that stuff very well in the first place.
Yeah.
Right.
Or I think it's probably the opposite. It's that those points are probably in the retained set, and so removing them doesn't do much. Like, let's say you're all the same person, removing one of you doesn't, like, I still can generalize you very well.
Right. Like you mean generalization covers them. You don't need.
Yes,
you don't
yes,
need
yes,
that one.
yes.
Yeah.
Yeah, so the effect of unlearning on the same person
Yeah.
that's already in this that won't affect much, and so the distance between doing nothing and fully unlearning them is small because they never contributed very much. This is important, so it's good that we're stopping now because the rest of the talk is going to be built on this measure. Yeah.
Maybe we missed something, but why is this very probability?
Yeah. Sorry,
Oh, it is not probability.
it's
Okay.
not probability. There aren't many typos. This is one that I didn't know about. I apologize. This is KL divergence. Oh, it's a histogram. So yeah, it is probability, but this is a histogram of KL divergences.
Could you explain that one? Why is it the best you can do?
So this is technically not the best you can do, but this is what if you fully retrained a model,
Okay,
which is perfect unlearning, right? Like if I like just fully retrain the model without you in it, there's nothing better I could do in terms of unlearning quality. And we wanted to say, how would our measure look for that?
so here the KL divergence is between the Oracle models.
Yes, and that's the reason why it's not zero is because even the
Yeah,
same,
atoms.
exactly, yes.
Is this just like one oracle versus all the others?
Yes, exactly. Again, like these two, we're going to talk about actual unlearning. I'm just trying to contextualize, like, these are baselines. These are like baselines. Cool. So we've kind of talked about what is success and what even is unlearning and what we're trying to do. Let's start getting into the meat and potatoes. Like what?
Hold on for a
Yeah.
second.
Please.
Why wasn't that second graph all the way slammed to the left at 0? Wait, so
There's like
Yeah.
some variance between.
but now I understand for the middle histograms in the previous slide, right? You'll have some distribution, right? And then if you use that same distribution for both,
But you're
Then-
not using a distribution. You're using a single point.
you have a single point, right? But you have a distribution over models, right? So that single point is going to have some histogram over models, but then you have the same set of models for both. So it's the same histogram. The KL divergence would be 0, which is why I'm wondering why for every point it's not just slammed at 0.
Imagine your unlearning algorithm produced like a distribution of margins that's like, bimodal, and it's either this guy or this guy. When you actually pick a single unlearned model, it's going to predict a
One or
margin,
the other.
one or the other.
Right.
And so
And then so you'll have some histogram in the middle, which is one or the other, right?
the unlearning algorithm here
Yes.
is pick specifically one. So it's not pick the whole distribution. It's pick
oh.
specifically one unlearned algorithm.
Oh, okay. So I'm because I was confused by saying such that I is an N. So the histogram is not actually overall.
No, it is. I think the thing that is maybe confusing is that it's saying load a oracle, specifically one oracle, and that's your unlearning
Oh.
algorithm, not load like
Oh, but
each time you load a different oracle.
I see, but you're comparing one oracle to all the rest of the oracles.
That's right.
And then it leads to this.
Yes.
Okay.
And this is an important point. Yeah.
Okay, I get it. I mean,
Great.
if you got rid of the symmetry, something like the middle thing looks different.
That's right.
Okay.
That's right. Well, all you need to know about this is a good thing to think about. There's a lot of work that goes into unlearning evals. At this point, if you don't want to think about it, you should think of it as a measure in output space on specific points between your unlearned models and your retrained models. Okay, so let's talk a little bit about like existing methods. In the convex setting, it's like not solved, but it's kind of solved. There's these basically, I would point to these specific two papers. There's descent to delete, which basically says that if you take your new model, your model, and you just do gradient descent for long enough on the retained set, it'll just forget the other stuff. There's a couple more caveats, but it's nice. It's just like you can get a theory bound on this because it's convex, and it just like will go to the bottom. There are ways to do this more efficiently, but like let's talk about the more interesting case. Generally, the existing methods are some version of these really two things. There's a couple other tweaks, but I want to focus on these. There's gradient descent and there's gradient ascent. Really, these are the first two ideas you might have. You're like, I'm going to keep training on the retained set, or I'm going to do gradient descent, which is I'm going to take my forget set and I'm going to go in the opposite direction of where my gradients are going. And then there's combining them. And then specifically, there's this algorithm called Scrub that iteratively just does both of these. It doesn't exactly do gradient descent. It does like KL divergence ascent, but it doesn't. At the core, nearly every single unlearning algorithm and all the ones that are doing well or even half decent on unlearning benchmarks are just combining these two things. And if you look at the data, they don't actually do well. Again, I actually don't want to actually look at the data there. Let's philosophically ask like, why might these not work well? And you come up with these like symptoms of what's going on. You're like, okay, gradient descent, it actually takes too long in the non-convex setting. Like maybe you would eventually unlearn everything if you just trained on the retained set, but it's taking a long time. And really this is because they have no reason to forget. They're just like, you're just kind of hoping that if you like keep telling them about, you know, Jaden, they're gonna forget about Alex. And then gradient ascent, it's actually like it's a different problem, but it's philosophically doing the inverse of optimizing something is not the same thing as not contributing it. These are just philosophically not the right thing. But even if it was, like the bigger problem is when do you stop? The nice thing about things that go like this is that there's a single thing at the bottom if you're going down. But there's an infinite number of ways to go up, and you truly don't know when to stop. And that the stopping point is very important. I am positing, and I think there's good evidence, that the root problem with all gradient-based methods is this missing targets problem. You don't know when to stop. And so like, let's take a look at Scrub, that algorithm that it's going to do gradient ascent for the first roughly 3 steps. And then it's going to be doing gradient ascent the whole time. On the y-axis, we're plotting unlearning quality. This is basically how well does that data point fit to the distribution of oracles, something very similar to our Clam score. It's effectively, rather than a KL divergence, you're fitting to a Gaussian, and you're doing this over time. And these red lines are points that get unlearned and then get worse over time. And you'll see for validation, it kind of like stays in the like reasonably unlearned because you're not really doing anything in the validation set. And the retained set, similar, but on this forget set, you like have points that are unlearned at one point and then they become less unlearned because on that gradient ascent step, you've gone too far. And you don't know when to stop because some points you haven't gone far enough and other points you have, like these points clearly benefiting and these points clearly getting hurt by doing gradient ascent more. And you don't know how to differentiate them, and so that's trouble.
Just to make sure if I'm
Yeah.
understanding. So what you're saying is if we continue to do gradient ascent, first it forgets and then it relearns the same thing.
Not relearns, but the unlearning quality gets worse in that
Okay,
it's like it forgets and then it does even worse.
okay.
You can imagine like, let's say I know English, and then you're like, forget Harry Potter. and like I take enough steps that I have forgotten Harry Potter, and then I keep going, and then I forget English.
Okay.
That last one, the where I forget English, is not close to the distribution of things where I never learned in Harry Potter. It's different in another way.
Okay.
So I've gone too far in
For the, I think I'm confused with the, why is it necessarily bad for the retained data set to have a decreasing unlearning quality? What does unlearning quality decreasing mean for the retained?
So we're taking the same measure. The measure is for this data point, how well is it fit by the distribution of oracles?
What's the similarity of the series for the data?
It's something very similar to that. It's, you know, if the margins of your data points fit a Gaussian, which they generally do, where in that Gaussian are you sitting?
Yeah, focus the word unlearning quality.
Yeah, it's also the opposite direction of the clown score. But this is actually a probability. This is fitting how well that individual data point is to what the oracles are doing. And in this setting, the thing you need to know, if you trust me, is that up is good. This is time, and things go up and then down. That's the like takeaway. And then for those two, they don't really change, but when the algorithm doesn't even really work on them, so like that's fine. And they're also like high enough that you don't really care.
Two questions. So what are multiple lines representing? And the second question, is there a regularized?
Multiple lines, each line is a different data point. So you're asking like this picture, like I have this picture of you, picture of Alex,
So different data points in my forget set.
in your forget set, in your retain set, in your
Yeah,
validation set.
okay.
And this, it's actually very important to plot multiple points, because an important takeaway, if you ever work in unlearning, is that different points unlearn at different rates, and different forget sets unlearn differently. And so because Scrub is applying the same algorithm to all the data points indiscriminately, and has the same stopping conditions for all of them, like you don't know when to stop. Does that make sense?
Yeah.
So you sort of set the, you know, set the groundwork here by saying, okay, there's gradient descent, the gradient ascent methods. So one of the things that we've been trying to do in our lab is, well, we do concept unlearning rather than data unlearning, but
Yeah.
But we've been trying to, so, you know, we sort of agree that gradient ascent methods are inherently unstable. It's not a well-formed objective. You can't, it doesn't make sense to not optimize around.
Mhm.
In a lot of the situations that we're in, you can define a gradient descent objective, sort of cuts a notch in the thing that you're trying to forget, so that you're actually driving the model towards,
Yeah.
you know, modified distribution with a notch in it.
So
Right.
yeah,
Uh-huh.
sorry.
Is that so?
We're gonna get to something somewhat similar, not
Okay.
exactly notch cutting, but
Uh-huh.
I like this idea. I'll say gradient descent is like, you really, if you're doing unlearning, you really want gradient descent based methods, because hyperparameter tuning is very hard. This algorithm is the best algorithm, but it requires the most finicky hyperparameter tuning. And because evaluation is an expensive operation, if every time you want to unlearn something, you have to like do a whole hyperparameter tuning, and you don't trust that it's going to work for something else, this is an unusable algorithm. And so everyone generally agrees you would much rather have a slightly worse algorithm that requires less hyperparameter tuning than a better algorithm that does. And so my opinion is avoid gradient descent based methods, because gradient ascent based methods, because of their hyperparameter tuning. And so this notch idea that turns it into a descent problem is generally like I think the right direction. Okay. And we're kind of gonna get into sort of a notch cut. No, it's not. But can you cheat? Let's define like oracle matching. Let's say like, okay, we're gonna try to do whatever we can to come up with the best unlearner. And so I'm gonna just take I'm gonna say, let's say I have sample access to a fully retrained model. And then I'm just gonna do gradient descent on that, on the outputs of that prediction. And this kind of like immediately solves this missing targets problem. like all the numbers go up. Some of them go down. Actually, good question why, I'm not sure. But it's like truly on the scale of like 0.01% of the population, maybe less. Those are good questions. They don't even go down that far. But look at how nice this is. They all go up. And it's because we've given a very well-defined like target. It can't overshoot it because now we're doing only gradient descent, no ascent, no real hyperparameter tuning.
You're just turning it into a student teacher model here.
Yes, this is knowledge distillation. Yes,
Right.
absolutely. What's up?
No,
Okay.
Who's the teacher?
Here?
Yeah, well, that's why it's cheating, right?
Yeah.
Because you need a teacher.
Yeah, that's
Right,
right.
yes.
This was more of a joke of just philosophic, like morally it's wrong.
So it's not a teacher, it's somebody who's,
This is the Oracle, the retrain model
Yeah.
is the teacher. We call this
It's the
Oracle
tutor.
measuring. But we have no oracles in life, is I guess the okay. What do we have? We have data models. We have this thing called like data models are these things called predicting predictions. This slide might be okay. This is a weakly opinionated nomenclature slide. You guys probably actually are exactly the wrong people to show this because you're probably more informed on this. But there's influence functions and there's data models, and there's also like data models TM, where influence functions, as I understand them, what people mean by that is when one data point, how it affects the weights. Data models is how one data point affects another, the loss on another data point. And then there's specifically a data models method called data models, which is very annoying, which is kind of this regression that I will breeze through in like 20 seconds. But as an example, like data models are a data model, track is a data model. This is weakly opinionated, don't sue me.
so actually, probably most of the people in the room don't know what all these different things are. And
Okay.
if it's important,
So,
you could, Yeah.
So we're gonna go into data models. I'm just trying to, and I'll explain in a second. I think this side is really just trying to split between, there's this thing called influence functions that are related, that are how much training on this affects your model, is how I interpret this usually. But what we really care about is how much one data point affects the model's loss on another data point. And I'm going to explain. Yeah, so basically, data models is this paper. There's this paper roughly a couple years ago that they're like, can we predict predictions? And the answer is yes. And what you do is you like take you take your data set and you,
Sorry, can you use one?
yes,
You say, like, data models. Different.
I would say this is all attribute. I mean, so again, opinion. I would say this is all attribution. I'm trying to make the distinction about data point attribution, where the question is really, if I trained on the data set S, my predictions on point X compared to if I never saw Y. If I never saw Alex, or my predictions on Jaden, this is different than what I think most influence functions are. I think you could reasonably call both of those attribution. I don't know what people do.
just to.
Yeah.
make sure So data model gives you that number,
Yes.
theta of x, s of x minus theta of s.
Yes.
And y of.
And if you have, I'm a little bit hiding something, and let me jump 2 slides. Specifically, this data models predict the difference in margins, which is like just a measure on, it's this number, it's the probability, it's like the correct class in one situation subtracted by the softmax or it's the softmax of that probability divided by the total sum of the probabilities, logged. But you have to do it for a specific class, like basically how confident are you that it's the picture of a cat? And for most of these, and it's a subtle point, they don't really emphasize this, but in data models and track and these data models papers, they are asking for the influence of one data point on another data point's correct class prediction. How confident are you in that direction? But what we're to like immediately tell you what it is and then change it. We're going to be doing, we want this for each specific class. I'm going to change the way the data model is structured because I'm allowed to make a prediction, not for the correct class, not for your influence on the correct class, but on a specific class. So it's like training on you. How much should you change the prediction on me on that I look like a cat, that I look like a dog, like for each of the classes that exists. And I think I have a diagram here of it's like really what I'm trying to get to and what I'm able to do is say, you know, here are the original model logits. Here are the counterfactual logits. The red is the delta. It's like, you know, so like the dog goes down. Like if I didn't train on you, what is the prediction on me? My data model is trying to learn this specific delta thing. And that's how they're used often. If you read the papers prior to this work, they're not computing a vector, they're computing just the scalar of the correct class. And the point of that, why are they doing that, is they're just trying to ask what points matter. They're not trying to ask how much do they matter in specific directions. Okay, but now you've kind of like already solved your problem. If you have access to data models, because I actually will show you the slide. If you have this, right, you have this like, ignore the rest of it. You have how much Y contributed to your prediction on X. I can sum up all of these guys in my forget set. And then I have like a reasonable approximation of how much of what my data set looks like literally just subtraction. Where?
Because some of the logics also go down, right? So it should be absolute value, right?
If training on you makes me look more like a cat and training Alex makes me look like less like a cat and I remove both of you, then I should
Okay.
look like equally
They
like a
kind of
cat.
like balance each other.
Yeah, so actually it's not absolute value.
Okay.
That's why these can go negative. It is a good question of, you know, this thing is doing a lot of work here.
Mhm.
The group influence of something is not the same as the sum of all the individual influences. Turns out they're close enough. Both in our work and in previous work, they've just like kind of seen this. But very fundamentally, these are not the same thing. That's where that approximation is coming from.
I think your theta can be like anything, like any model.
Any model you want. Any model you want that you can reasonably use a data model for.
So I'm not familiar with it. So I've heard of the data model that you're going by. I'm not familiar with it. So is it practical? Is it something? that you
Yeah.
sort of give it a month?
Data models trademark. It's on the order of magnitude of like 10,000 retrainings. Not
10,000 retrainings.
Not practical. Track
Yeah.
is an approximation of this that does worse, but reasonably is on the scale of 10 to 100 retrainings.
Were you on the track paper?
No.
Okay, but this is Marjorie paper.
Yes.
Yeah.
The short answer is this is not reasonable for the thing I'm about to tell you guys. It's not going to be reasonable for large language models for two reasons. One is even doing 2 retrainings is too many retrainings, let alone 100. The other is this whole point that I was making, this like subtle point thing. You have to do it for each class. You have to make a data model for each class. In classification, CFAR 10, you have 10. At least the naive a way to transfer to a language model to a classification is each vocabulary, and it's 50,000. That's just too many. But to like at least show you some results, can we just replace our oracles with data models? And the answer is, yeah, it works. It's pretty good. Where this is scrub, this is just the forget set plot. This is oracle matching, and this is data model. It's like, they're pretty similar. They're not perfect. And we'll show like more results in a second, but first point is that we've gotten like this impractical algorithm, because it's so computationally expensive, does work. This plot takes a moment to explain, because we've now condensed our CLOM scores one more time. If you remember, I'm just going to show you the CLOM score again. Right, this is CLOM. What we're going to say is like, okay, this is still too much information. Like I don't want to have to show an entire histogram for everything. So I'm just going to report to like 99th percentile. And that's it. That's the one flattening again that we're going to do. And here is our like headline plot, where gray is existing methods. This dashed line is doing nothing. And then the let's start with the y-axis is CLOM, down is good. This is your forget set. This is your retain set. This is your validation set. The x-axis is training time. It's rescaled according to like full retraining. These red dots are just fully retraining your model. This is like the benchmark. It's going to work optimally. It's this bottom right corner. It's perfect, but it also takes the most amount of time. The gray lines are the things that exist already, and they kind of don't work that well. They're kind of, maybe they work well on validation and retain, but they don't work here. And if you care about some combination, this is just the weighted average. And then you have our methods. Data model matching, it just like plummets down very quickly. Yeah, the like, this is the headline takeaway. It's that we like are Pareto optimal. This is an empirical result. To like immediately slightly qualify our results, it's that like we're plummeting down at unlearning time, but you have to do this really big pre-computation cost.
of the data model.
Yeah, of computing the data model. The nice thing of why is this somewhat reasonable is that you only do this once and you can like forever. Like every unlearning request does not add more compute. Because at least for a long time, those influence functions, they just work. They like continue, you can continue to stack them. And so, yeah, I just wanted to show this one plot, just slightly different, but it's just adding track data model, which is another data model matching, and it like doesn't work as well, but it works pretty well. That's all this plot is showing. I won't focus on this. We're actually basically done. There are plenty of future directions. I think this is like, I view this more of a science paper than an engineering paper. I think future directions are things like oracle matching. We're using an oracle, but it's not actually optimal. We haven't proven that it's optimal. We just kind of guessed. There are certainly better ways that you could do this knowledge distillation from the oracle. And so doing work even in that theoretical setting would improve the data model setting. Group influence is definitely not the sum of leave one out influences. This becomes a bigger problem as you compose unlearnings. Like it's very different. It's going to be different if I say I'm unlearning all of you versus if I unlearn one of you and then I unlearn the next and then I unlearn the rest. Understudied or basically not studied. I think this is the more interesting area, the like making it scale. Can you compute, what are influence functions or attribution functions that you can use? How do you scale this to language models? All great questions. And then the last question that I think is like, I kind of just threw at you as I said, like, this is a good measure of unlearning quality, is CLOM. I think it's the best one we have. I can argue this quite well, but like, it's not good. I think we can do much better. And sorry, it is good, but I think we can do much better. That is technically the talk. There is what is now question time. And these are pictures I took.
Thank you, Ray.
Yeah, so sounds like the problem to scaling language models is like the class number, not like the size of the model. Is that, or is that the size of the model also a problem?
It's a multiplication, right? Because you have to do a data model for each class. So if each data model is already, even doing one data model on a language model would be too much. People haven't done it really. And then doing it 50,000 times would be also too much.
Yeah, maybe, what is like the data model that you're,
Uh,
yeah,
So for each class, you need to store the whole model. Like for each class, you need to store the whole language model. Because I saw that you were doing SGD on theta, right? The language model itself. So yeah, here you are doing SGD on theta, right? L theta.
you're doing it on the logit vector. Sorry, this is a vector
So I mean,
of
Yes,
size
yes.
class.
I guess the question is actually the data model itself is a model. Is
Yeah,
it the language model itself, or is it
no,
something
it's
that is
it's like a linear regression model, but in practice, it's actually, yeah, it's the way many of these things work is the size of the model is something along a linear regression. Basically, what you do is you take, I'm going to do an okay job of this. You take your data and you randomly sample a bunch of subsets of it. They're like 50 percenters, say like 10,000. And then what your goal there is you're going to say like, there you're able to say, there's going to be points that include point X, say Alex, and have U in it, and a bunch of models that don't have U in it. Half of them are going to have U in it, and then a quarter of them are going to have U and Alex. And so by like conditioning on those, I'm able to make those predictions. And what they do in this problem is they like, I'm not going to do a great job of explaining it, but they turn this into a big hyperplane because this is a binary vector. And for each, right, like it's a bunch of ones and zeros, and you have like 10,000 of them. And for each point, you ask for the prediction on that point for the models that included it and the models that didn't include it. The short answer is it's not a language model, it's a regression problem. Even and track is as well. The slightly more nuanced answer that you weren't asking is, in practice, there are two things that are the output of these like engineering things. Like in theory, we can talk about it, but in practice, there's the model, but you actually just pre-compute the like n by n matrix of the influence of point X on point Y. And to compute the influence on a point outside of that validation set is more expensive than the original operation of that generation. Was that like a sufficiently roundabout answer?
I think that's helpful. So it's also dependent on the like the trained data size also, like.
Yes, this,
Since they're trained on. That's
yeah, that would be right, but that's the easiest of these to resolve because you're choosing to make this n by n matrix, and if you wanted to make it a smaller subset, you just have to pick the ones that you're going to subsample. And so that's actually where my point of like, Oracle matching isn't perfect. What points are you going to Oracle match on is a good question. What points, how do you, like knowledge distillation, the whole point is that you like need fewer points. And so asking the question of which points do I want influence on would reduce the need for this n squared matrix.
Sarah asked something related, but I think like it's like this question and also
Can you use that?
when you
But I can,
You can do that.
oh, I can see it.
whatever, yeah. And so like if you go to like scaling to language models, you talk about like, oh, like the naive thing is like talking about like every single like if you're trying to like unlearn every single token or something as there are like classes. Like on one end, I'm like sort of not convinced that say if you like unlearn the token Ryson, you've like actually successfully like
Yeah,
the model can probably just like reconstruct this in the aggregate of the other tokens. And then like this is like sort of related to like, what's your take on how do we actually remove the concept of, say, ricin?
Yeah. So I think there's actually two important thoughts in your question. One is like, what is an example? In privacy, to like kind of redirect your question to like where I think this is a much more troublesome worry is differential privacy. If you're familiar with it, is this like guarantee of like neighboring data sets that like your one data set, the output of your model is not too dependent on any one data point, but like what is a data point? What is your definition of neighboring? Is just a philosophical question that we know how to answer in picture space. We don't know how to answer in language space. It's the same question for unlearning. It's like, what does it like? Yeah, what does it even mean to be trying to do concept unlearning as like a very acute thought process, thought example? In GDPR, this like legal thing that Europe has that is why you have to answer all these cookies, and they give you this right to be forgotten. You can go to them and you can say, please delete all my data, and please delete all pictures of me. And I actually just have to like tell you the concept. Like I don't forgive them all the pictures of me. They have to do it regardless. So there I'm asking for the concept of me to be unlearned. And this splits up the problem of unlearning into two. If you are doing data unlearning, there's like, you've now broken into two parts. There's like finding the data set you're trying to unlearn, and then there's the like actual data unlearning. If you wanted to go the data unlearning route, if you wanted to go the concept unlearning route, I think you're not going to be able to do it in any kind of statistically meaningful way, but you can still do it in like a human meaningful way of like, if your goal is to remove the concept of ricin being used in to murder people, like I strongly think, and I think a lot of people agree, unlearning the concept of ricin in the concept of murder is not the right way to do that. I don't know if I like actually answered your question.
There's a sort of a maybe a theoretically happy way of stating concept unlearning that we're sort of settling on, which is maybe if you say you have a classifier for data or output that would represent the concept that you're trying to unlearn. So like here, like your setting is you've got a data point that you're trying to remove, right? And so, but you could imagine a problem setup where you say, oh no, I have a classifier for data points that I would like to remove. And then you're sort of left with this interesting question of like, oh, can I go straight from having a classifier to getting a model that would result from removing that concept? Does that make sense without
Yeah.
having to
Yeah.
stop at the data points? And
So I think that's actually exactly the like kind of distinction that I'm trying to break of there's finding the points you want to unlearn and the actual.
right, the classifier is finding the point.
Yes.
So suppose somebody gave you the classifier, right? Then the question is, oh, maybe there's a class of unlearning methods which use the classifier as a starting point.
So here's my thought on something that should be done related to this. It's okay. Let's start with the philosophical problem of I have this data set trained on people, and there's 2 pictures of me, or like there's 100 pictures of me in it, and I ask to be like I give it a data set with 50 pictures of me, and I say unlearn this. Philosophically, what do I want to do with? Okay, I'm gonna say 40, so the numbers are the same. What do I want to do with the other 60? Like this is a philosophical question, and I think this actually puts data unlearning and concept unlearning on the same spectrum, where I think there's a dial here, which is how concept unlearning versus data point unlearning, and that is going to be some threshold on the influence of one data point on points in the retain set. Basically saying my forget set is not the forget set, but it's all points that are within some influence function of my forget set. And I think that is how, and why does that put this on a dial? It's because if the influence function is anything, then like that's forget everything. Like that's
It might be more complicated than a dial in the sense that like, oh, like a different classifier might generalize differently like on different, axes, like, oh, maybe you train you want a classifier with a certain inductive bias, which really doesn't matter, it doesn't care.
That's
The
right.
image is blurry, you're wearing different clothes.
That's right.
But maybe it's very sensitive to your personal identity that
That's right.
your
Your choice of
yeah.
influence function. Like the other axes that you're proposing here, I think, is
Right.
your choice of influence function, not just the threshold over which you.
Right.
But this is how I would combine data and concept learning. I think often concept learning is it's a human desire that we have to do this thing, but it still.
But I think that you can, so that's what I'm saying, is that I think that you can turn it into a theoretical problem, say, yeah, there's this human judgment of what the classifier is.
Yeah.
But let's say somebody said, we've debated this as humans, and we think that this classifier is it. But now you've still got this mathematical engineering problem of, all right, I've got a classifier. I'm going to treat the classifier as the oracle of things that I wish the model had.
That's right.
Right. With then there's this problem.
I guess I was also thinking like whether we want to go in and do this at the representation level directly, and maybe that's just the same thing as the classifier question. But wouldn't it be nice if you could go into the model and just remove all of the stuff? Like, would that be more satisfying than doing it at the data level?
Okay. Yes. I don't. So there is some work that shows that sparser models are easier to unlearn, or they unlearn better. And the pseudoscientific explanation here is that sparser models have more monosemanticity. Like empirically, sure. I think this is not. I don't love this of just saying let's just make the model sparser and then. But this isn't making the point of then if we have monosemanticity, then you can just truly remove that neuron. I think that won't happen. But that's an opinion. I think it's at least reasonable to make the statement of empirically, if you induce monosemanticity through sparsity, then unlearning becomes easier because I don't know, it's easier.
But can I invert the question the other way? So you've been playing with data models for a while, working with this stuff. So do you think that, in a sense, the data model is the answer to interpretability? Like it tells you the structure of how models are generalized, and it tells you the structure of what models are learning from the data, right? That if you understand the structure of the data model, you understand the structure of generalization in the model.
Probably not. I think for two reasons. One is computationally it's very expensive. I think that cannot be ignored. And the point of interpretability is to be useful. If it's too expensive to work on a language model, it just isn't useful. Philosophically, whether or not you want data point to model or data point to data point, I think I probably want more data point to data point at the end, but I think I don't know. This is a vibe.
You think it's not capturing the right thing?
I think it's a good abstraction. I think unlearning is a really good use case for it. Influence functions are a reasonable use case for data set curation, but what are the goals of interpretability? They're safer models so we know what they're going to do, and this is a related but ultimately orthogonal goal here. Did I answer? I'm kind of giving you a vibes answer.
Yeah, give me a vibe. Yeah.
I think one great project related to this is taking these other influence functions, specifically but converting them to be a data point to data point, and then, but given that influence functions are cheaper to compute because you can just do them on the final model. If you have some kind of access to that, can we do a much cheaper unlearning through data models? Sorry, yeah, data models not trademarked, just the kind. I think that would be a pretty good direction for unlearning. But
You mean unlearning using influence functions instead of unlearning using?
Yeah, I think what I want is gradient-based data models, which don't exist right now. I want a method that is cheap, that will give me a half decent influence of one data point on another. I don't think this exists right now. I could, and I could just be.
But that's sort of, I mean, that's influence functions, right? Isn't that, or?
Yeah, the reason why
I understand.
the reason why I'm like being cagey about it is because I had this like weak opinion slide
Sure.
where I kind of
Oh, I see.
explicitly said that it wasn't that, but this is not a formal definition. This is just the literature that I've read seems to kind of follow along these lines. But I think I think one great direction for unlearning would be a gradient-based data model that is data point on data point influence. And I don't think I've seen this, but maybe I just, read it a long time ago and forgot about it, unlearned it. To like, unpromptedly just talk about safety. I think there is little evidence that unlearning can be used for safety training. I think like especially the fact that you can introduce things in context for large language models. You can just like imagine, I don't know, I'm kind of coming up with this on the fly, but like your model knows about like chemistry, and it knows about like things you can fit into suitcases. Like you can tell it to like build a bomb in context, and it'll like do it even if it removed all the things from training. This was on the fly, and maybe it's a bad example.
I guess like in cases like this, it's like if I already know how to build a bomb and I teach the model in context, like why do I care?
The model knows more than you, and so maybe you know some things, but not like how to do an integral or something. I don't know. Like
Okay.
you have to do an integral, you don't know how. That's like a pretty reasonable world you might live in.
So you like teach it the concept of an integral and hope it like generalizes to.
There's
or-
this issue, right? Like if you have this huge scratch pad and then if the model needs to figure out how to make a bomb along the way, maybe it'll say, oh, well, I don't know how to make one, but I've got a few terabytes of scratch pad. I could probably work it out.
Yeah.
And thank you, Roy.
Yeah.
Really appreciate it.
Yeah. Thank you.